that we've already been talking about. Right, so one of the, I think, most important things to walk away from when you're done with algebra is not that you can do all of these pieces individually memorized. Right, the reality is that I have a math degree, and sometimes students come back to me and say, Mrs. McKinney, can you help me with this? And I'm like, oh my gosh, I haven't done that forever. I just need to really quick look at your notes and remind myself, and then I'm good to go. And that's realistically how we will function as adults. Right? We have something attached to us that basically allows us to Google and look up anything. The more important piece is that we need to be able to know what we even need to begin looking for. Right? If you forget how to do something, where would you even start? Okay? And we've talked about a ton over the course of this entire year of math. Right? We've talked about being able to deal with linear functions. Right? That was a large piece of first trimester. Right? Graphing linear functions, they make a line. Finding inputs and outputs. Right? How we write the equations of lines, the different representations of lines. Okay, we've looked at quadratics, solving quadratics, graphing quadratics, how we know that we're dealing with quadratics. And we've looked at exponentials. They're all different type of functions. Okay, but it doesn't do you any good if you want to remember how to graph a quadratic if all you know is that you're talking something about graphing and you have no idea what ballpark you're even starting in. Right? It's sort of hard to narrow down and Google it if you don't even know what you need to Google. And that's sort of what we're talking about today. Okay, this is looking at the less specific pieces and sort of stepping back and looking at this umbrella of functions as a whole. What are some things I would know to be true if I know I'm going to get a pay raise every year that's 2%? Okay, well, I know if I'm getting a 2% pay raise, it might start off growing really slowly, but eventually that's going to start to pay off because it's going to start to really skyrocket up. Okay, as opposed to getting a job offer that's going to pay me a $2,000 pay raise every year. Okay, well, that might sound great to start with, but eventually in the long term, that $2,000 pay raise isn't going to be near as much as a 2% pay raise. Right? And the reason why I know that is because I know exponentials start off slow but start to grow quickly. I know that constants or linears are consistent. I know that exponential graphs do this. I know that linear graphs do this, right? There's a point that the exponential is quicker than, right? It's all of those sort of basic details that we know about them without looking at the specifics of each individual problem. Okay, and that's where we're sort of at today. And the three different categories that we're going to be looking at is linear, quadratics, and exponentials. Those are the functions overall that we've looked at all year. Okay, so when we're looking at these, we're going to talk about some things we know to be true in each of these categories. So let's start with linear. If we have a linear function, what do we know is going to be true about its graph? What do linear functions always look like? Donovan? Nope, that's not linear, that's exponential. Jake?
There's a straight line.
A straight line, right? It could be going uphill, it could be going downhill, but we know that a graph of a linear function is a line. Right? It's extending both ways for forever, it's a line. What do we know to be true about a linear equation? What does a linear equation always look like? Can someone give me an example of a linear equation? number is linear.
Okay.
Okay, y equals 4 is a line. This is linear. Someone give me another example of a linear equation. Will?
Want to be like y equals 3x plus 4.
Y equals mx plus b form is linear. Standard form is linear. How do we know that these are linear? What actually makes them linear as opposed to being quadratic? What did we say the word linear meant when we were talking in our polynomials unit? It has a degree of, not 0, a degree of 0 is constant, a degree of 1. Okay, so we know that linear functions, linear equations, have a degree of 1. A degree says that when we look at the exponent on a variable, it has to have an exponent of 1. Right? Which means we're only seeing x to the first power. I shouldn't say or. Obviously, we're not going to see that exponent of 1 sitting there. We'll just see x and y. But what we can't see is x to the third or x squared. Right? We cannot see an exponent of 2 or an exponent of 3. Linear functions, x to the first. Okay. What do we know to be true? Oh, this is a tougher one. If we were to look at a linear table, it does have x and y, but we also used x and y tables with quadratics and exponentials. This is a tough one. But you know me, I'm just going to keep waiting to see what we come up with. Yes, Donovan?
Don't we have to do the negative b over 2?
Nope, that's quadratic.
Oh.
Isaac? What do you mean by the slope? Not sure? That is a key. What if I say this? I'm going to tell you that this is a linear table. They're going to have ordered pairs, no matter what type of function it is. That's what makes it a function. Yes, Jake?
There's like a pattern.
What do you mean by a pattern?
Like each one goes up by the same number.
Okay, this right here. And the reason why it has it is because a linear function has a constant slope. Right? We are consistently adding or subtracting or whatever the same amount. It's consistent each and every time. Which means as long as over here we're increasing by a consistent amount, right? Over here we should be increasing by a consistent amount. Because, right, this would be a slope of 2 over 1, 2 over 1, 2 over 1, 2 over 1. It's been a long time since we looked at that. That was Algebra 1-1. Right? But when we looked at tables, we could find that rate of change, that slope. It was always consistent no matter where we looked. Okay, so in our table, we're going to sort of see this constant increase or decrease, depending on which way the numbers go. Ooh, what a word problem. What if we're reading a word problem on a state test? Right, the state test is just going to give it to you in a completely random order. You're not going to be able to say, oh yeah, this is chapter whatever in Mrs. McKinney's room, so that means I must have to write this type of equation. Because let's be real, we all do that. Right, when we are given a test in a high school class setting, we're all going, oh, well, this is the unit that it's over, so this is the information I know I need to be pulling from. That's not how real life works, which is also why we give you that review portion. Okay, in the real world, right, we would have to decide, well, what situation is this? Is this linear? Do I need to be writing something like this? Or do I need to be writing something like I did in the POD today? So how do we know if we're reading a word problem that we're going to write something that's linear? We did this in the POD and across the board, we all seem comfortable writing that as exponential. What told us that this was exponential? Say it, Kate.
What the value will be in 10 years.
I could still do a value in 10 years if it was a linear. The what? Say it. The percent. The fact that, that's what I thought you were starting to say before. I didn't know.
Yeah.
Right? The percent changing if I have something and it increases by 2% each year, is it always increasing by the same amount? No, right? Because 2% of a new value is a different number. So for something to be linear, it needs to be increasing or decreasing. Same thing is up here. At a constant rate. For something to be happening at a constant rate class, we're talking about something happening per item. Right? I'm making an extra $200 each year. I'm selling something at $8 per shirt. Right? It's constantly the same thing, no matter whether it's the first time I'm doing it or the 100th time I'm doing it. Now, the value might not be the same, right? Selling one shirt is a different amount than selling 100 shirts, but each shirt holds the same value. Okay, that is linear, that constant rate happening. Okay, are we okay there? Any questions with linear? Okay, exponentials is the next easiest, so that's what we're going to do next. What's a graph of an exponential going to look like? Yeah. This, I don't know, a swoop, that was the word I make up for it. Some type of swoop going on. Right, it can go either direction, it can go up or down. Something that's some type of swoop, that's exponential. I really feel like you probably shouldn't go to your upper level classes and be talking about a swoop, but I don't know what else to call it. Maybe I should converse with my other algebra teammates and see what they use. What do we do next? Equation?
Yeah.
It's gonna be awesome when this video gets posted. What does an exponential equation or an exponential function look like? Is this exponential? No, because we just said these were linear. These were linear because they had x to the first power. What do our exponential equations have? Will? Nope, that's not. Hold on to that thought because you're going to need that. That's just a different category. Donovan, what do you say?
X to the 0.
Nope. Isaac, what do you say? And what's that last piece that you said? Right? What's the exponent in an exponential? X. Right? An exponential has an exponent of x. Right? It's exponential because the exponent is our variable. So this could look in various forms, right? Whether we're doing growth and decay and we have that sort of parentheses to the x power, whether we're doing basic graphing and we have y equals 2 to the x, and that exponent being x is what makes it exponential. Okay, so for an exponential table, I need to give you some info here. This is a little bit trickier, just because we haven't talked about exponentials as much to sort of see. Okay, we can tell that a table